Hello everyone, this is Hunter. This episode is a little bit different because we had a whole lot of stuff to cover. When you hear this noise, it means I've cut something out to keep the episode reasonably timed. You can find all those sections on the Deep Cuts companion to this episode.
You're listening to Encyclopedia Podcastica, a podcast from the Silicon Valley skeptics. Prepare your mind.
Welcome to Encyclopedia Podcastica. I'm Hunter Perrin.
And I'm Matt Courtney.
Encyclopedia Podcastica is recorded in front of a live studio audience. Woo! That is our wonderful studio audience. So, Matt.
Yes, Hunter.
On August 24th, 2016, Proxima Centauri b was announced to have been discovered by the ESA.
Ooh.
It is a planet orbiting our closest neighbor star, Proxima Centauri. Proxima Centauri is a red dwarf star. It's part of the three-star system called Alpha Centauri.
Is that really just like a little people star? Not dwarf.
Alpha Centauri? Or, you mean because it's a dwarf star?
Yeah. Sorry, bad joke. Okay, keep going.
Yeah. It's in the same way that Pluto is a dwarf planet. It's actually not in the same way at all, because stars don't have orbits to clear.
Yeah.
Well, I guess they kind of do, but they don't clear their orbits. Would that make all stars dwarf stars?
No.
Except for like the
brown dwarfs. They're dwarfs. But I think that just has to do with the size.
The classification is different between dwarf stars and dwarf planets.
Right.
But yeah. So Proxima Centauri b is at minimum 1.3 Earth masses, which makes it very similar to Earth in size. Hopefully, at minimum.
Right.
It could be bigger, which we'll explain why later. But it's orbiting in the habitable zone of its star, which is a really big deal, because that means water can exist as a liquid on the surface of this planet.
Which is really important.
For life.
Yes.
Not really important for anything else.
Probably not.
Like if you were ice, you would probably hate the habitable zone because you'd just melt.
Yeah, it'd be melty.
Luckily, we're not ice.
Correct.
But yeah, the habitable zone is considerably closer to Proxima Centauri than our habitable zone. Compared to our solar system, it is well within the orbit of Mercury. So it's really close to the star. Since it's a red dwarf star, so it would make sense that that habitable zone would be closer since it's not as hot as the sun.
Right.
But that also means it has a year of a little more than 11 days.
Wow.
So it like rockets around this star.
That's like shorter than like a dog year.
That's true. And it is 11/365ths of our year.
0.25.
That's true. Or about 3% of our year. Unfortunately, that means it's probably tidally locked to its star, which means it always presents the same face to its star, meaning it probably gets really hot on one side
is that
and
a
really
happy
cold
face?
on the other side. It's like the man in the moon.
Right.
Just a face.
Same face. Okay.
But yeah, so I wouldn't get my hopes up about living on it, but there may be life there.
Maybe.
Which would be pretty fucking cool if there were life there. And life as we know it could actually exist on, even if it's tidally locked, it could exist on this little ring around like the middle of the planet. So a little ring, like one side is hot and the other side is cold. And in between the two is a ring.
Yeah, it's right on the edge of where light turns to, day turns to night. Basically, except they don't really have a night and day. Yeah,
it's just one side is permanent day and the other side is permanent night.
Right.
Unless it's tidally locked like Mercury is, which actually has day and nights, because it's tidally locked in a ratio to the sun. So its year has a ratio to its orbit that is like, I think it's like 2 to 3 or something. So like every 3 days is 2 years or something. Or 2 days is 3 years or I don't know.
Rotation.
Yeah, so it is technically tidally locked, but it's not tidally locked in the same way that our moon is, where it always just shows one face.
Okay. But it actually might be better to be tidally locked like that, because then you'd have like a constant temperature and stuff.
It would be better to be tidally
Possibly.
locked like that.
Right.
Because it would help the planet distribute heat, which
Right.
would be the problem with maintaining life, because life generally doesn't like melting.
No, it doesn't.
Unless you're an extremophile, then
Right.
you might actually like melting.
Wouldn't one side really close to the sun get really, really hot and the other side get really, really cold?
Yeah. That's what we're talking about. And in between...
Crazy weather?
You would have crazy weather, actually. Yeah.
Yeah.
Like,
Well,
you would have
you'd just have
you'd
like
have
constant,
insane winds.
constant wind?
Yeah. 'Cause
Well, except now how would
one
it go back to
side-
the other side?
It would be the side facing the star would get really hot, and all the air would expand. You'd have a low
Right.
pressure zone,
And
then
push out to the cold side.
Yeah,
But the
cold
problem is,
side-
how would
the cold side would be a high pressure zone, which would rush into the hot side and then heat up, and it would be like a convection oven where it's just like convecting. Or I guess not a convection oven, like a convection cell. You know, where
Right,
stuff
right.
was convecting all over the place, and it would be crazy weather. It would not be a fun place to live anyway, unless you had a really big sailboat.
Maybe.
Maybe. So, Matt,
Yes.
tell us the history about planet hunting. Ooh,
Now,
our first
so,
planet. Okay.
First planet, Mercury. Closest planet to the sun. That one was actually, we don't know when it was discovered because it's been known since ancient times. Actually, the Assyrian astronomers associated it with the god Nabu. Now, I don't know if that means that they actually called it Nabu or if it was just they thought it was that god or it was somehow otherwise associated with it.
Isn't Naboo the name of a planet in Star Wars?
I think it might be. Anybody? Yes. Yeah, we got some Star Wars geeks in here. I'm not enough of a Star Wars geek to know that.
Shame on you.
I know.
Isn't that where Amidala, or whatever her name was from?
Yeah.
Princess.
Natalie Portman.
Natalie Portman is from Mercury, little known fact.
Did not know that. But it was the Greeks that actually ended up naming it Mercury.
That would make sense because Mercury is a Greek name.
Yeah, Greek god of running or something. I don't know.
He was a messenger god, right?
Yeah, I
He
think,
had wings on his feet.
That
yes.
would be the Romans. Hermes was the...
Oh.
You guys just got...
So
Our
wait,
audience
that
is
makes-
smarter than us. Every
Wow.
episode.
Wow.
The planets are mostly named after the Roman gods, the
Yeah, most of them are named after the Roman gods, aren't they?
Venus, Aphrodite.
So that's an error in my notes.
Mm.
I should have known that.
Our audience is so smart.
Technical difficulties.
They tried to cut us off.
They were getting sad that they're not as smart.
Shut the whole thing down.
We're done.
It's been a good run.
Right. So the next one is Venus. And it's actually the brightest planet in the Earth sky. Night sky, of course. And it was also known by the ancients. So it was so bright that the Romans actually named it Venus after their goddess of beauty. So am I good there? That was Roman.
That's correct.
Okay. Okay.
The Greek name for it.
I don't know. Well, I don't know if did the Greeks actually name it? I don't know.
But the Greek equivalent.
Would be Aphrodite.
What?
Correct.
Yeah.
Nice.
Go team.
I need
I
a
like
dinger
Venus
here.
better. Like it's just a shorter name,
I agree.
but otherwise it's fine.
And it rhymes with clean us.
What? Were you going with something else?
Nope.
No. Okay.
Not going with anything else.
Okay.
I think it was a sexist joke because women are from Venus. So it's
Just like Mars rhymes with.
I'm not sure why they would want to be
Cars.
from a planet that has like a overpowering atmosphere and where everything like melts on the surface.
Where you'd be crushed to death and melt
Yeah.
almost instantly.
But
Yeah.
that's kind
How
of
hard it is to be a lady? Think about it.
okay. Fair enough.
you ever tried to shave your armpits? It's quite difficult.
Oh God, it's awful.
Never actually tried that.
Nor have I.
But I just want to point out the Babylonians called it Ishtar. And the Mayans, they had a nice idea for Venus. I thought it was actually the brother of the sun, which is kind of funny when you have the Romans naming it after the goddess of beauty. So it doesn't really know what sex it is, but yeah.
Are you saying a brother can't be beautiful?
Well, it's the Romans specifically it's the goddess. not the god of beauty.
Maybe it's non-binary.
Okay, maybe. I don't know.
I think we can let the planet determine its own gender.
Don't pressure the planet. No pressure.
Venus has a lot of pressure.
Exactly.
Tons of pressure.
Tons of pressure.
I'm happy you walked into that joke that I left open for you.
Is it literal tons of pressure? It is, right?
I don't know.
Yeah,
I didn't
it's
actually
like
look
15
up
tons of pressure per.
I just know
square
like the first
foot or
like
meter or
5
something.
probes or something we sent to it like melted and died on the planet.
I mean, doesn't Earth technically have literal tons of pressure?
Yeah. So Venus also has like even more literal tons of pressure.
Wait, but well, how would you determine it? Because it's per square inch or square centimeter or whatever.
Per square, whatever area we need to make a ton.
Oh, okay.
That's my unit of measure.
Fair enough. And then, of course, the next planet is Earth, and we've known that one a long time. But I did want to point out it was.
What did we name it?
We named it Earth.
What did we name it after? Little known fact: we named it after dirt. Earth means dirt,
Right. I should have known that.
and in most other languages, it's just named dirt.
It's just dirt.
Yep.
Well, it wasn't until October 24th, 1946, that we actually got the first picture of Earth from space. So the first Earth selfie. I thought that was interesting.
Was it flat?
No.
Well, the picture was.
The picture was flat. We actually used the modified V2 rocket.
Score 1 for the science team.
Yay, science. Science.
1 zip.
Thomas Dolby, yeah.
Take that, flat earthers.
And next planet is Mars, named after the Roman god of war. I don't know the Greek god's name. I should know it.
Aries?
It's Aries. Ooh.
Aries?
Yeah.
Oh. Is that why in The Martian, it's Ares that goes to Mars?
That's correct.
Oh, that's awesome.
I assume.
Okay.
I met Andy Weir at Comic-Con. I got him to sign my website.
What?
Yeah. I brought a tablet, and I had him sign my website.
Okay.
MartianFarmersOnly.com.
Is that like
It's
a dating site?
Yep. And guess how many profiles it has?
One?
Mark Watney. He's the only Martian farmer.
Wow.
He's a very lonely man.
I was going to call you a dork, but then I remembered where I was.
Yeah. We're at a podcast called Encyclopedia Podcastica.
Yeah, it's pretty, kind of dorky.
Dude, we're dorks.
I've been okay with that for quite a while.
Oh.
I don't know about you.
I'm just coming to grips with it.
I'll be okay, son.
Now our listeners are going to think you're my dad.
Yeah, no. He's much younger than me. Hunter is much younger than I am.
I'm not much younger than you. Like,
Aren't
you're not old enough to be my dad.
No. But I'm like 10 years older than you.
I guess technically that would make you old enough to be my dad
Let's
in
not do
very
that.
certain circumstances.
No.
Moving right along.
Yes,
Moving
please,
on,
next.
Jupiter, again known by the ancients, named for the king of the Roman gods. Yes.
Wait,
okay.
let me guess. Zeus is a counterpart.
That's correct.
Bam!
All right.
That's the one I know.
Okay, moving on to Saturn.
Woo!
Again, also known to the ancients, and this is I feel like this is like the worst named planet. Romans named it after the god of agriculture.
Oh, I thought it was named after the car company.
No, I don't think that quite works.
I think at that point it was a chariot company.
The chariot company. Saturn chariots. Probably or possibly one of the reasons they named it after agriculture. The Romans didn't actually know Saturn had rings, which we all know now today, thanks to, among other people, Galileo. But the rings of Saturn weren't actually discovered until 1610, when Galileo pointed his telescope at Saturn and saw the rings, but he actually thought they were a series of moons first. It wasn't until 1655 that Christian Huygens, that sounds right, Huygens,
Huygens.
finally discovered that it was a ring. And he also discovered Titan, Saturn's biggest moon, at the same time. So,
oh my God, Titan is such a cool moon.
It is.
Did you know that on Titan there is weather just like on Earth? It is the only other body in our entire solar system that has.
Well, there's weather on other planets,
or like
because Jupiter has a lot of weather.
A cycle is what I mean. Like you know how we have a water cycle, like rain, and then it evaporates. Yeah. And then
what does the cycle do?
The rain runs down into the
the ocean,
and the oceans, and then it evaporates, and then it goes back up over the mountains, and so same thing on Titan, except instead of water, it's methane and ethane.
Right.
Which here, it's so hot here, it's so boiling hot here that they're gases, but over there it's a nice balmy like negative 200 something degrees Celsius. So methane and ethane can be liquid, and there's a methane and ethane cycle.
Wow.
It's so cool.
That's pretty cool.
The only other planet that has rain, or not planet, body. The only other body in the solar system that has rain. Really cool.
Yeah, that's pretty cool. And the next one is we don't know how to pronounce this one. Because it's
Uranus.
Uranus or Uranus.
It's
or
Uranus.
Uranus was a new pronunciation.
I heard Uranus a while ago.
Uranus.
I think they're grasping at straws there. It's it's Uranus.
Right, Uranus. We'll go with Uranus.
Unless you're like 5, then it's Uranus.
I thought we were 5 here.
Uranus. Okay, now we got over that.
We're over it. It's actually barely visible from Earth without a telescope, but it wasn't actually discovered until December 1690 by John Flamsteed. Flamsteed? Sounds about right. Yeah. He actually thought it was a star and named it 34 Tauri.
Even back then, they came up with crappy names for stars.
Really, yeah, bad names. March 13th, 1781, Herschel, he thought it was a comet, but noticed the orbit was nearly circular, finally realized that it was a planet. So we find it. We found that planet. Now, Neptune is probably one of the most interesting finds, I think, of our, local solar system planets, because it wasn't actually discovered by direct observation. It was discovered by mathematics.
Fuck yeah, math.
Which is pretty cool.
We forgot to talk about what Uranus.
This just in.
So Uranus, the counterpart to that, our wonderful audience has pointed out to us, is Hades.
Yes, the god of the underworld, I believe.
Wait, that doesn't make sense, because there was another planet I thought was named.
Yeah, wasn't Pluto?
I don't know.
Uh-oh.
I overstepped my bounds there. My apologies.
Uh-oh.
Yeah.
I think we need to consult the great Google machine.
Okay. Can I go on to Neptune while we're doing that? Okay, so people noticed Uranus, all of those, was its orbit was deviating from its predictions, and they're like, what's going on? And in 1835, Halley's Comet actually it reached its perihelion, which I believe is its furthest point, right, from the sun. It ended up there later than predicted. So there's something like messing with the orbits of the planet and the comet. Between 1843 and 1845, John Couch Adams crunched the numbers on Neptune and crunched the numbers and found Neptune basically through mathematics. But he was basically ignored. And there was another guy named Urbain Le Verrier. He also did Leverrier. That sounds right. It's French, right? His French name. So he did the same calculation and also came up with the coordinates for or the existence of Neptune. He was ignored, but he talked to, I think it's Johann Godfrey Galle, and in September 23rd, 1846, Johann actually pointed a telescope up there and found the planets where it was predicted. Finally found it. So we have Neptune.
Oh, by the way, I looked it up, and Uranus is the Greek god. And Salus is the Roman counterpart to
and
the
what
Greek
is
Uranus.
And what is the god of?
Uranus means sky or heaven. Was a primal Greek god personifying the sky.
Interesting.
So god of the sky.
God of the sky, not this guy.
God of this guy.
This guy. He just went around with like thumbs pointing at himself. This guy. So
who's got two thumbs and is a god?
This guy. Uranus.
And also Neptune, his counterpart is Poseidon.
Yes. And they're gods of the water or oceans.
Yep.
Correct. I don't know. I don't think there's any oceans on Neptune. It's another gas
Probably
giant.
not.
But
Don't think gas giants have oceans.
Romans didn't know about that, so I guess that's fair. Well, it wouldn't be discovered by the Romans, so I don't know why they named it. It's 1843.
I think we just kept with the tradition.
Okay, just like picked a random god.
Yep.
So extrasolar planets. So these are planets that do not orbit the sun, but orbit other stars out there somewhere.
Or rogue planets are also extrasolar.
Or rogue planet. That's true.
Just planets that
not,
aren't gravitationally bound to a star.
I did not mention anything about rogue planets.
That's fine.
We did find a few, but most of what I looked at was planets orbiting stars.
Yeah, that's fine.
Of various types. So the first possible extrasolar planet was actually found in 1988 around Gamma Cephei, I think.
Gamma Cephei?
Gamma Cephei. I think that's a star.
Yeah.
Now, it's not officially the first extrasolar planet found. I think there was evidence for it, and one or two people may have thought it, but it wasn't actually confirmed until 2003. So that's not the official first one. The official first planet found was in 1992. So if you most of these places you'll read about extrasolar planets, the first one they'll say is in 1992, because we found first clear evidence of an extrasolar planet, and it's Alexander.
Alexander?
Yeah. Walls is something that starts with W. Wolska. Yeah.
Wolska.
And the other guy is Dan Frail, which is a lot easier. Dale Frail. It's a lot easier to say, even though I still screwed it up. But they found a planet orbiting a pulsar, and the pulsar is PSR B1257 plus 12.
Good old PSR B1257 plus 12.
Yes. It's in the constellation Virgo, if you were wondering.
I was.
Yeah. But the first extrasolar planet found around a normal star was in 1995. I think it's Mitchell Mayer and Didier Quazell or Quelaz.
It could be Mikel Mayer.
Could be Mikel Mayer.
And Didier Queloz.
Much better at saying the names. You should be like saying all the names. I did actually practice most of these names, and I'm still screwing them up. But they use the wobbling star technique, which I'm sure you'll talk about. I think that is the official name of the
It's
technique.
not, but
Oh, okay.
It's colloquially.
Yeah, when I was
method.
actually reading it, it literally said wobbling star technique. I'm like, okay, that sounds good. It was around 51 Pegasi, and the actual planet was 51 Pegasi b. With the planets that we find around stars, we tend to name them. I don't know why, but it's always starting with
It's
B.
because the star itself is A. So the star would be 51 Pegasi A.
But we don't
and then
say
the
that.
first
We just call
planet
it
would be 51 Pegasi B.
Right. Until we give them other names, but their scientific name or something is that. Unless we have the weird number one, which I don't understand. But anyways, it's a hot star hugging gas giant. So it's a really big planet. It's it's not that big. It's half the size of Jupiter, but it's pretty big.
That's big.
That's pretty big, but it's only half the size of Jupiter. But it's orbiting very close to its star, 51 Pegasi, and it only has a 4-day orbit.
Whoa.
Really
fast.
That is
very close.
Very close. And it's because it's so close is why it was found so early, even though it was the second one, third one, depending on how you count it. In 1999, we found the first multiplanet system with 2 additional planets found around Upsilon Andromeda, which is actually a binary star system. So it's 2 stars orbiting each other with at least 3 other planets orbiting, I believe, both of them. It's not individually.
That's so fucking cool.
And I think actually since then they found even more around that particular system, more planets orbiting it. So it's like crazy number of planets.
It's like in Star Wars, the Tatooine, right? Was the one that orbited a binary star system.
Yeah.
Another Star Wars reference.
Yay. In 1999, again, there was the first use of the transit method, which I'm sure Hunter will discuss.
Yeah. Transit method is awesome.
But the planet is HD 209458b in the constellation Pegasus. It actually orbits so close to its star, the atmosphere of the planet is being stripped off like continuously. And it forms a tail like a comet. So it's a planet that actually has a comet-like tail.
Wow.
Yeah.
That's kind of what happened to Mars.
Yeah. Except I don't think Mars had like a tail.
Technically it did, but you probably wouldn't be able to see it with the naked eye.
The vestigial tail.
I don't think that's how it works. But it was found by David Charbonneau. Charbonneau. He's important. He keeps popping up. The other guy, Greg Henry, I think is the only time he shows up. But they both made independent observations. They both found it separately, basically. That happens a number of times, which is interesting. On April 4th, 2001, the first planet found within the habitable zone of a star. And astronomers from Geneva University found it around HD 28185b. And it orbits about the same distance from its stars as Earth does from the sun. Unfortunately, it's 6 times as massive as Jupiter, so can't actually live there.
There's probably no water on it anyway.
Probably not.
Not liquid water.
Right. In October 2001, it was the first atmosphere found on an extrasolar planet, and it was teams led by David Charbonneau, comes back again, but also Timothy Brown, and they used the Hubble Space Telescope and found it on HD 209458b.
These star names are just
great
mind-bogglingly ridiculous.
2004, first direct image of a extrasolar planet. I assume you'll talk about direct imaging as well.
Yep.
The planet is 2M1207b, and infrared light was used to detect the planet.
So I gotta ask here, did they run out of Greek gods or what happened?
I think they did, because there's thousands of planets and
they could have gone
billions
to
of
Indian gods.
stars, and I don't think they could, even with India and all their like crazy
Hindu gods.
The Hindu gods.
They've got.
Do they have
Is
thousands?
it hundreds? I thought it was thousands.
Well, if there are thousands, there are hundreds.
Well, they should have just like moved on to like Star Wars references and Star Trek.
There's infinite Star Wars references, right?
Right. Not quite infinite, but there, could be like hundreds. I mean, who would not want to live on a planet named Yoda?
But also,
would it be a swamp planet? Didn't Yoda live on a swamp planet?
But what was the name of the swamp? It was Dagobah, right?
Yeah.
Yeah.
But if we started naming planets after Star Wars references, does that mean Disney would own all those planets?
Oh, that's a good point. I don't think so.
Disney already owns Pluto.
Well, there's that National Star Registry where you can get a star named after yourself or your loved one.
I think it's such a joke.
I think that's a scam. Moving on, February 2007, we found possibly found water on an extrasolar planet. HD 189733b, using the Spitzer infrared space telescope. It was one of the first 2 planets actually observed by that telescope after it was sent into orbit. In May 2007, we actually mapped an extrasolar planet. Now, when I'm talking about map, it's not actually like land
like
map.
Google Maps.
No, it's not Google Maps.
Not
Although
Google
that'd be
Maps.
really cool. Maybe we can like get Google to make a map of this. It was again HD 189733B. If you don't recognize it from earlier, and the map actually shows the temperature of the cloud cover on the surface of that particular planet. So, yeah,
that's really cool.
Yeah, and again, it was David Charbonneau, but also Heather Knudsen, I guess. K should be silent, right?
Yeah.
Knudsen. Moving on, November 2008, with first extrasolar planet imaged in visible light. Fomalhaut B. So they actually had like a name.
Yeah.
Where it came from.
The real name.
Yeah. That I probably also screwed up.
No, that was right.
Fomalhaut.
It looks like Fomalhaut.
Yeah, Fomalhaut. Anyways, that one is 3 times the size, or 3 times the mass of Jupiter, and only 25 light years away. And an optical telescope was used. So 25 light years away, we could like technically send a probe there.
That would take a
really long time, but yeah.
We could send a probe there, but we wouldn't be alive when it got there.
Oh no, definitely not.
I mean, we definitely wouldn't be alive when it sent any data back.
Yeah.
Yeah.
Even if it got there.
How would you even send data back?
At the speed of light, unfortunately.
Yeah. In March 7th, 2009, a big event in planet hunting occurred as the Kepler Space Telescope was launched. And it is a space telescope specifically designed to find planets, particularly Earth-sized planets, and named after Johannes Kepler. In January 2011, the first Earth-sized extrasolar planets were found. Yay! By Kepler, which is now they're calling him Kepler. This is Kepler 10b.
That's a much better name.
It's getting better. I assume that means it was the 10th planet found or something. The B would be like the planet, I guess. Maybe it was the 10th star it looked at or something. Anyways, it's 1.4 times the size and 4.6 times the mass of Earth. So it's actually denser, I think, than Earth.
Yeah, that would be much denser.
I think it's much denser. It's kind of hard to tell because when you do like 1.4 times the size, I assume that's talking about diameter. So when the diameter increases, it's a cube times the mass, right? So, but I don't think it would go up to 1.4 times.
Actually, yeah, I don't know. I think we would need to look up a density function to be able to answer that. And
yeah, probably. Anyways, if this planet is actually orbiting 20 times closer to its star than Mercury orbits the sun. So it's orbiting very close to its star. So it's the right size, but not in the right position. Too hot. In April 2014, we find the first Earth-sized extrasolar planet within the habitable zone. So we have the right-sized planet in a habitable zone where liquid water could actually exist on its surface. It's Kepler 186f. It's 10% larger than Earth. It orbits a star half the size of the sun. It's 500 light years away, so we're not going there anytime soon.
Well, honestly, we're not going to the one that's 25 light years away anytime soon.
Like 500 light years. That's just way off. So that's all of the first planets that I have written down. We did mention one that's even closer. That's a extrasolar planet in a habitable zone.
Yep, the one we just found.
Just found.
Yeah, around Proxima Centauri.
Right. But as of the 1st of September 2016, so the first of this month that we're recording this episode, we have 3,518 known extrasolar planets. Of those, there are 2,635 planetary systems. So some of them are obviously multiple planets around a single star. There's 595, actually, multiple planetary systems. And again, of those, we found more than 100 that are the same or similar size to Earth. And of those 100, there are 9 that we know of that are in the habitable zone.
So book your tickets now.
I don't know where those 9 are. We did discuss a couple of them. But there you go. In general estimates, we believe, after all of this planet hunting that we've done, that there's likely 1.6 planets for every star. So 1.6 bound planets, I should say. So planets that are actually orbiting a star.
So one planet and then a sixth of another planet.
And a sixth of another planet, just like a hunk, little over half of another planet. It's like a Pluto.
Oh.
In the Milky Way, and 1 in 5 sun-like stars likely have an Earth-sized planet in the habitable zone.
That is astounding.
Yeah, so it's 20%.
It really makes me wonder, like, why haven't we heard from other life?
I don't know. Maybe we should talk about that in another episode.
I would love to talk to alien life. That would be so fascinating.
It'd be so alien.
Yes. Yes, it would.
Yes.
So I want to tell you about the science of planet hunting.
Yes, Hunter, tell us about the science.
Or exoplanet detection.
Okay.
Well, I guess not just exoplanet detection, because we can detect our own planets. In
Yes.
fact, the easiest way to detect a planet is by standing on it.
Really?
Which we detected Earth that way.
Wow.
I'm detecting Earth right now.
Yes.
Well,
I'm
I'm detecting
kind
an
of-
office floor,
Yeah.
but
There's probably Earth under it.
Yeah.
Yeah.
No, it's carpet all the way down.
There's no turtles? So the second easiest way to find a planet is to look at it, which,
Right.
you can just look up and you'll see planets.
Yes.
You may not
we discussed.
realize that they're planets, as
They
we
look
didn't
like
for
stars.
a while.
Yeah, so we didn't
Yeah.
know. But they
Um,
wander.
Yep. And then you can also look at them through a telescope, and then you will realize that they are planets and not stars.
Hopefully.
And if you've never taken even like a cheap telescope out just to look at Saturn, do it.
Okay.
Saturn is amazing. You will look.
I think honestly, I have not done that.
Really?
Yeah.
Oh,
Because I've seen
Okay.
I've
Remind
all of
me.
my astronomy.
Remind me.
Okay.
I'm gonna grab my friend's telescope. We're gonna go out and look at Saturn.
Okay.
Because Saturn, just seeing it with your own eyes is so amazing. The rings are so beautiful. And even when you're seeing it on, a not very expensive telescope, just the fact that you're seeing that planet and its rings is just so amazing.
Cool.
It really takes your breath away.
Right. But looking at Pluto is kind of boring.
I don't know. The New Horizons pictures are
That's true.
breathtaking.
It has a heart. Has a little heart on it. Not really. It's kind of heart-shaped.
It has a Rorschach test on it.
That's true.
So you can see whatever you want
pretty
to
much
see.
everybody thinks this is a heart.
Or actual Pluto the dog. Did you see that one where
No, I missed
Pluto,
that one.
There's like a picture going around the internet where Pluto the dog, the Disney character, is superimposed on top of Pluto the planet, and it's amazing how perfectly it fits into that planet.
My concern with that situation is that Mickey Mouse is a mouse and he has a pet dog. I want to throw that out there.
But he has Goofy's supposed to be a dog. So he has a friend that's a dog, but he also has a pet dog.
Yeah,
It's really confusing.
a variety of questions that on a particular podcast, but
So the next easiest, I guess.
So what did
Maybe
we did?
not
We did look
easiest,
at,
but-
and we look at through telescope.
Yep.
So the next
But the next
one,
way we can find them is to find them through orbital mechanics, which is how we found
math.
Yeah, how we found
Math.
Neptune.
The power of math. We
yeah,
talked about
and
that,
then-
how that worked. And finding Pluto. Well, not really finding Pluto.
Accidentally
Finding Pluto that way. Yes.
And possibly finding another planet if that pans out, which
Planet X.
I think would
pans
be
out.
pretty cool, but I'm skeptical.
I'm not going to hold my
so-
breath because
yeah.
it's probably going to be years, and I would
Yeah.
die holding my breath for years,
minutes really.
minutes.
So then our first attempt at planet finding, exoplanet, finding planets around other stars was called astrometry, which is where you watch a star very closely, and you watch it to see if it makes tiny little circles in space as it orbits the barycenter of the star-planet system. It requires extremely precise tracking of the star's position.
So this is finding stars or finding planets extrasolar planets, right?
Yeah.
Right.
Yeah. So you
couldn't really look at the sun and see it wobbling, and well, you kind of could, but
yeah, you could. You absolutely could.
But we probably found all of them that are easy to detect that way.
Well, with this method, we didn't actually find anything. We found a lot of false positives.
So we found a lot of stars that are like wobbling.
Yeah, there were a lot of false positives.
Okay.
But even though it's the oldest method of
so what do you when you
exoplanet
when you talk
hunting,
about like oldest, like how old is this method?
This has been around since the 18th century.
Wow.
Yeah. When we first
so it was
kind of pictured this method and thought, hey, let's try this, but it didn't actually pan out.
It was like almost 200 years after we started this, but we actually found an extrasolar planet.
Yes.
Wow.
But even though this has never discovered a planet,
yeah,
it has characterized previously discovered planets.
Okay.
So it is a reliable method, just not nearly as reliable as many of our other methods. So it's generally considered unreliable enough to not pursue it.
Okay.
So yeah, throughout the 18th, 19th, and 20th century, people tried to use this method, and it just produced so many false positives, and we weren't able to confirm.
In the 18th century, they were like drawing this or something, like doing.
They would keep track through. Yeah, they would write it down.
Okay.
And keep track of the position on paper.
It wasn't like they were drawing the star.
And then eventually photographic plates were used, which
that would be better.
Yeah. Which was much more precise. But the problem is it wasn't precise enough. The measurements have to be so precise that even our best ground telescopes today aren't precise enough.
Yeah.
So then our first method that actually detected a planet was the pulsar timing method, which you mentioned this planet that we had detected that was orbiting a pulsar. And the way that we detect planets orbiting pulsars normally spin at a certain frequency.
Do you want to describe quickly what a pulsar is?
Oh, yeah. A pulsar is a neutron star. So it's the remnant of a star that has collapsed and gone supernova. So it's a neutron star that's highly magnetic, and it's spinning around, and it's firing off these jets of radio along its north and south pole, but it's spinning on a different axis than the north and south pole. So when the jets are pointed at us, that's when we can detect the radio emissions, and then it spins around again, and then we detect it at that same point each time. And they're very, very precise. They're very regular in their periods.
Right, and it actually looks like from Earth that it's a flash. Like they're
pulsing. It's a flash of radio waves.
Looks like they're pulsing, which is where pulsar gets its name from. Yeah.
So they're usually very regular, but if they have a planet orbiting them, they can cause a little bit of variation in the timing. Because the orbit of the neutron star around the barycenter of the star-planet system causes a little bit of variation in when we receive that pulse.
Okay.
And in 1992, that was the first method that was used to detect an extrasolar planet that was confirmed.
All right.
And then we have pulsation frequency, which is a very similar technique that uses pulsating variable stars, which will swell and shrink. So they're not pulsars, but they pulsate by swelling and shrinking. And do
we know why they're doing that, or
we do. If I can remember correctly, it's because of the way that the stars will fuse at different rates depending on. I'm not sure actually.
Okay.
I believe it has to do with the convecting outer layers of.
Okay. Maybe we can
they will shrink and become more opaque, and then they will expand and become more transparent, and that expansion increases the brightness, and then there's this cyclical process that causes them to shrink and become opaque and expand and become transparent, and that just repeats, and it makes the star pulsate in how bright it is.
Okay.
There are a few different kinds of variable stars, but
well, we can look it up and maybe do a waifu later if that's not
possibly
exactly right.
Yeah. Then there's also polarimetry, or polarimetry. I'm not sure how that's pronounced, but that is measuring the combined light of a star-planet system and looking for polarized light. So light emitted by stars is normally not polarized.
So it's like they're wearing shades or something?
So in case you don't know what polarized light is a wave, so it travels in these up and down motions. You know, the electric wave.
Transverse wave, I think, is what it's called.
It's
it's not a compression wave, which is sound.
Correct.
Right.
Yeah. You have the electric field moving in one direction and the magnetic field moving in the other direction.
Right.
Because that is what creates an electromagnetic wave. And normally those directions will all be scattered. They'll be pointing in every which way. But when light reflects off a surface, the light will reflect so that all of the light is waving, is moving up and down in a particular way. And that's what's known as polarized light.
Okay.
And if you have these tiny little slits in a just some, if you like in sunglasses,
anything
if you
that blocks,
anything that blocks a shade. If you have basically blinds, but the blinds are very, very, very small.
Right.
That will only allow polarized light in.
Right. And shades basically
light that's going in that direction.
Like
normal shades don't, but polarized shades will do that to block light that's reflected off of horizontal objects like a car's hood or a lake.
Yeah.
So the light emitted by stars is not polarized, but when it reflects off a planet's atmosphere, it becomes polarized.
Okay.
So we can detect a planet through that polarized light. But it's only able to detect planets with high albedos, which is the amount of light that reflects off a planet.
Okay.
And planets that have atmospheres, because it needs to reflect off the atmosphere.
Okay.
But it is able to detect the composition of the planet's atmosphere through spectroscopy. Because you have light that's coming off the atmosphere, whatever that atmosphere is composed of will absorb certain wavelengths of that light. But it's never actually detected a new planet.
What?
Yeah. Much like the astrometry, it has only detected previously detected planets.
Okay.
So let's move from that one to the most successful way of detecting planets.
All right.
Transit photometry.
Okay.
This is commonly referred to as the transit method, and it is amazing how we find these planets with this method. So what this does, what we do for this method is we measure these very small dips in brightness when a distant planet eclipses its host star, which is known as a transit, when it passes in front of the host star relative to us.
Okay, yeah, between us and the host star.
Yeah. We are able to accurately detect the planet's radius because the dimming of the star is directly proportional to the size ratio of the planet and the star.
Right.
So we know what size the star is. We know how much it's dimming, so we know how big the planet is.
That's cool. So like a really big planet may like completely block it.
I don't think any planet would ever completely block the light from a star.
It will block a lot more than a small planet.
Yes.
And so, but that means that small planets are harder to detect using this method.
Not really. They'll both block light. So,
okay.
I mean, I guess they're a little bit harder, but not much.
Well, there's probably some margin of error in the calculation, so if it's teeny tiny.
Yeah, you do have to detect whether the star is just varying in brightness.
Right.
And the way you do that is just keep watching it if you see a transit, and if you see a transit again, then that's confirmation. So if you see transits
but if it's like pulsing, the star is pulsing like you talked about some stars pulse, that would still work.
Well, we know when a star is pulsing.
Okay. So it looks different than a transit.
Yeah.
If you see a star dim, how do you know whether that's a planet or like a dwarf planet, something else?
Well, dwarf planet would just be size.
Yeah.
Exactly the same.
Well, not size, but whether it's cleared its orbit.
Okay, fair enough. We wouldn't really be able to detect that anyways.
Well, a challenge you'd run into is if it's orbiting very quickly, right? We'd see a lot of dimming more frequently. But if it orbits every 2 Earth years, then it'd be tougher to...
Yeah, it would be.
And that's why we
much
found.
tougher.
Is that why we found like the ones that are orbiting closer? Like,
yes,
a lot more.
We
of those
find
early...
them. We find them a lot more often,
right?
Because we don't have to monitor the star for as long.
There's a big like worry in the community for a while, the astronomy community for a while, that like, oh no, we're only ever going to find planets that are right next to their stars, and they're not going to be any like Earth-like planets. And
yeah, I remember when people were saying that, but now we're finding Earth-like planets.
But now we can actually do it. So.
Yeah.
Oh wait, no, they're not that uncommon.
So we can determine the size of the star pretty accurately with its spectrum. So this gives us a method to pretty accurately determine the radius of the planet, but not its mass. But it also tells us more than just the radius of the planet. It tells us if the planet has an atmosphere, because the light from the star will be absorbed by that atmosphere to different degrees and different wavelengths depending on the composition of the atmosphere. So we can determine if there is an atmosphere and what that atmosphere is made of.
That's cool.
And this is some of the most crucial information to determine whether an extrasolar planet harbors life. If the atmosphere is full of oxygen or methane, those things normally don't happen through natural processes other than life.
What about Titan? Because didn't we talk about Titan having... Was it methane on it?
Titan has liquid methane.
Okay.
But you wouldn't get both methane and oxygen.
Yeah.
That's true.
So if you get both methane and oxygen, it's a pretty good indication that it might have life. It's not
true. Not guaranteed.
Confirmation.
Right.
But it's an indication.
So I think I already know this answer, but have we actually detected a planet with both oxygen and methane on it?
I don't think so.
Yeah, I don't think we'd have.
Mars has methane on it, but we also, like, that is most likely a chemical reaction happening between water and the certain type of mineral. I can't remember what it's called.
Okay.
But that's another way to produce methane.
Right.
That is not life.
Right.
I don't think we've detected one that has both oxygen and methane.
Okay.
If we did, it would be a pretty good indication that
that would be like
might
a
have life.
Big deal.
Yeah.
Like a big deal.
Yeah.
Yeah.
So we'll see that in the news someday.
Someday.
Yep. So a secondary transit is what happens when the planet disappears behind its host star. And that's how we can tell that it's actually a planet transiting the star.
So wait, how does that, like, how do we detect that? Because we're not blocking the light from the star anymore.
True, but the planet is reflecting light from the star that we can see. So we can analyze the spectrum when the planet is shown versus when it's hidden by the star to determine the true spectrum of the planet. And that'll give us both the composition of the atmosphere and the temperature of the planet.
Okay.
Which is also very important for determining if it has life.
Yeah.
At least life as we know it. So the Kepler mission launched in March 2009, as Matt mentioned. And the Kepler mission uses the transit method.
Right.
And it can monitor around 100,000 stars at once.
Wow. So it's just like pointed at like 100,000 stars.
Yep.
And it's just looking, waiting for these changes.
Yep.
To
waiting
happen.
for very minute changes in brightness.
Right. And
but
where
even
where is the Kepler telescope actually located?
I'm not sure where it's located, but
it's actually I think it's following the Earth's orbit, also in solar orbit. It's not actually
in one of the Lagrange points.
Something like that.
I think that would be the L3 point. No, L4. I forget which point follows. One of the points leads, and one of the points follows.
Yeah.
But yeah,
I thought that was interesting because that way it stays kind of stable. It's not,
Yeah.
I mean, it's moving around the sun, but it's
in
not.
those points, you don't have to put any energy into it to maintain that orbit.
Right.
In certain Lagrange points, you do need to put energy into it because they're not stable.
Right.
Like the L1 point, which is in between the sun and Earth, I believe.
Okay.
And then the L2 point, which is behind Earth,
okay,
relative to the sun. Those points you need to put a little bit of energy in to maintain orbit, but it's not much.
Right.
It's kind of like a bowling ball on the top of a hill. It's easy to keep it on the hill, but if it starts rolling down the hill, it's going to pick up speed.
Right.
Versus a bowling ball at the bottom of a valley, which would be the orbits that are in front of and behind our orbit.
Yeah.
But even still, Kepler monitors only a fraction of the sky. And we've already found thousands of exoplanets in just that fraction.
Wow.
So the next method is one of my favorite methods called radial velocity, or the Wobble Method.
Can I come back to Kepler real quick?
Okay.
I don't know if you'd read it, but so it was launched in 2009.
Mm-hmm.
By 2013, it actually had a catastrophic error. Basically, it broke in space. I didn't know if you read about that.
No, I didn't.
But we're still getting stuff from Kepler. What eventually happened, like it broke, and for a while they couldn't use it, so there wasn't data for some period of time, and it was like a stabilizer or something that broke. Well, scientists figured out that they could actually just correct it, like using, I think it was like solar wind or something like that, like adjusting it for that, and it still actually continues to move on, and its new mission is now called the K2 mission. Unfortunately, it's not. It's more limited on what it can look at now, but it's still actually ongoing.
Oh, scientists!
It was actually pretty cool.
So smart. So the Wobble Method uses Doppler spectroscopy of the spectral lines of a star.
So you want to describe,
which is where it's where you're measuring the light of a star, and as the star is moving away from you, that light will be a little bit redshifted.
Right.
And as the star is moving towards you, that light will be a little bit blue shifted.
Right.
Red shifted meaning the wavelengths get a little bit longer, and blue shifted meaning the wavelengths get a little bit shorter.
Right. It's
named
similar
after
to
the
how
two ends of our.
Right. It's similar to how when a train goes rushing by.
Yeah, you hear that.
Yeah, the higher pitch and then the lower pitch after it passes.
It's like higher pitched light and lower pitched light.
Yes.
In a way.
Or when Superman is running towards you, you see his blue uniform. When he's running away from you, you see his red cape.
It's not quite the same, but yeah.
That's exactly it. So you use this Doppler spectroscopy of stars to determine when they're moving towards you and when they're moving away from you. And that'll give you, if they're wobbling back and forth towards and away from you, that tells you that there's something in that system that's pulling on the star.
Right.
That's orbiting the star.
It's dancing.
And you can calculate a minimum mass using the binary mass function, which is the function that defines the mass of two objects, how they move.
Okay.
Two gravitational objects. But you can only calculate a minimum mass, not an actual mass. So the reason for that is if the planet has a high inclination, meaning you're seeing the orbit on edge, then the mass of the planet.
You mean like we're like the same angle as the orbit, basically, like it's like flat,
so
like
you
a pancake.
Yeah,
kinda,
you'd be looking at it like just a line,
right?
Rather than like a disc,
right?
So like when you look at an orbit like that, the planet's mass would be towards the minimum.
Okay.
Since you're getting all of the effect of the planet pulling the star towards you and the planet pulling the star away from you.
Right.
But if the orbit has a low inclination, meaning you're seeing the orbit more face on, like you're looking from the top down
so
at
it's
the
more
orbit,
like a disc.
Yeah.
Like we talked about. Yeah.
Then the mass of the planet would be much larger to have the same effect, since it's pulling not just towards you, but towards
some other direction.
Yeah.
Up or down.
Yeah.
Left, right.
So the smaller mass stars will be tugged more by their planets, and that makes them easier to find with this method. Planets with around smaller mass stars. And this is the method that was actually used to find the planet around Proxima Centauri.
Ooh.
So we don't know its true mass, but we do know its minimum mass.
Okay. So we haven't figured out, like, is there a way to later look and figure out what the inclination is?
You can use other methods.
Okay.
You can't always use them, but sometimes.
Okay.
But a fast rotating star will make the spectral lines difficult to read because half of the star, this is literally why, it's so weird, half of the star is coming towards you and the other half is going away from you. So if it's rotating fast enough, it actually makes it difficult.
Wow.
Who would have ever thought that, like, how fast the star is rotating?
Yeah, that would make it
difficult to find.
But it makes sense.
Yeah. And this method is good to about 160 light years for Earth and super Earth-sized planets. And it's good for like a few thousand light years for Jupiter-sized planets.
So the distance from here.
Yeah.
From Earth.
So we can look very far for Jupiter-sized planets and, quite far, but not that far for Earth and super Earth-sized planets.
Okay.
Where's the dividing line between Earth size and super Earth size?
Just anything bigger than Earth is a super Earth size.
Really?
Yeah.
I mean, it should be, but I thought like some of the things that I read, they
super
were
just
implying like within, if it's like 1.2 or 1.3 times the size of Earth, it was saying basically the same size as Earth.
I guess, yeah, you can call that Earth size.
Yeah,
I don't know if that actually has a definition.
It probably doesn't. But I got the feeling that it was like, if it was closer to twice the size of Earth, that it was more super Earth.
More super earthy.
More super earthy.
So our next method is gravitational microlensing.
Ooh.
Which is a really fascinating method. So this happens when a star passes in front of another much more distant star. The light from the more distant star can be bent around the closer star due to gravity, because gravity affects light.
Gravitational lensing and all that stuff.
And if that closer star has a planet, it'll contribute its strength to the lensing effect.
Oh, wow.
And we can detect that contribution. And that'll allow us to detect planets whose orbit is face on, like you're looking down at it.
You're looking at the pancake.
Yeah. You're looking at
Not
the top
the
line.
of the
pancake. But the stars and the planet need to be in a fairly specific configuration, which is pretty rare. Okay. So this means a lot more stars need to be monitored to find anything.
Okay. Like hundreds of thousands?
Yeah. And lensing events are short and they're rare. So they're even more rare than planetary transits, because it's not only does the planet and the star that you're looking at have to be in a specific configuration, but also a star behind it needs to be in a specific configuration.
Right.
And they can't be repeated, since that configuration isn't periodic like the orbit of a planet.
Right.
But still, how fucking cool is it that we can detect a planet using its host star as a giant space lens?
That's pretty cool.
That's so goddamn cool.
That's the most excited you've been this entire podcast.
It's like having a giant telescope the size of an entire star system.
Ooh.
It's so cool.
Can we use that with our Death Star to make like a star system size?
I don't have a Death Star.
Oh, okay.
Do you have a Death Star?
No, I don't. I just had to make another Star Wars reference,
Obligatory every 10 minutes.
Yeah. I think we missed a couple, actually.
You can make up for it now.
Just constant barrage of Star Wars references.
That's right, yeah.
So, I'm still really excited about that giant space lens. We can use this same effect with galaxies. So we can view really distant galaxies.
Really, really big.
Giant space lens.
Yeah.
We can view much further galaxies than we normally would, because these galaxies in the middle are acting like literally a lens.
Right.
Like they are a gravitational lens. So they're magnifying the light from these really distant galaxies, and we can see much further than we would be able to because of this cosmic lens.
Yeah.
It's so cool.
Unfortunately, I don't think we can use the galaxy size lens for detecting planets.
Probably not.
Probably not.
Unless it was a really, really, really big planet.
Right. But
in which case it would be a black hole.
Isn't that
not
like
a planet.
one of the ways they detected dark matter, though?
Through gravitational lensing? Yeah.
For a galaxy,
Yep.
Galaxy size.
Yeah, because if we can detect like how much matter is in the galaxy, and then if it's lensing more than what we detect,
then it should, yeah.
Then something else has to be there.
Right.
And that's something we just named dark matter.
Right. Because we can't
Doesn't mean we know what it is, but we know it's there.
Right.
Irony being there's more dark matter than regular matter.
A lot more.
A lot more.
So you'd think we would call the other stuff regular matter and our stuff light matter.
That's true. Well, we call ours baryonic matter.
No one calls it that.
I do.
Hunter calls it that.
And now we get to, in my opinion, what is going to be the best method in the future once we work out all the problems. Direct imaging.
Ooh.
Where you just look at the planet.
Wow. But
you
wait.
Just look at it.
Wait. Aren't stars like way brighter than planets?
They are.
Okay.
But if the planet is really huge and far away from the star, we can detect its thermal emissions. It has to be like way bigger and really far away, like bigger than Jupiter and very, very far away and very, very hot.
Wow.
Hot enough to emit a considerable amount of infrared radiation.
Okay.
So much so that we can detect that infrared radiation even around its host star.
Okay, this is using my pleb logic from our solar system, but generally when stars are farther away from the sun, they're colder, right?
Yes. So it has to be a planet that's producing its own heat.
I see.
That's why it has to be a big, like, super Jupiter planet.
Yeah.
Also, probably engage life.
Very, very hot.
Life.
Well, if they're generating their own heat.
Yeah.
Yeah. It would be infrared light.
But it wouldn't have any life on it.
Oh, life. I thought you said light. Correct. It would have no life. Not life that is anything like our kind of life.
Right. It's life, but not as we know it.
Not as we know it. It's life, Jim, but not as we know it.
Right.
We're mixing up our references.
I know.
We're supposed to be referencing Star Wars.
Star Wars, but Star Wars doesn't have that kind of reference.
So you can fix this problem, though.
Ooh.
You can use a coronagraph.
Wow. Is that how you, like, play Corona records or something?
My coronagraph.
I thought it was when you did math while drinking.
Oh, yeah. Yeah, that works also.
A coronagraph is a small structure about the size of a postage stamp. Well, actually, it's 3 parts. This is only one of the parts. About the size of a postage stamp that is placed within the structure of a telescope, in between the optics.
Okay.
And the...
Is it so it can be shipped? Because it's a stamp?
A stamp to space is very expensive.
Yeah.
You can't use a forever stamp for that.
Oh.
So this little structure is specially shaped to redirect the refracted light, the diffracted light away from the optics of the telescope. So it'll block some light from the star, but light will diffract around that. So if you've ever seen, like, if you put a wall in like a pool of water and you make waves at it, behind that wall, the water's not still. You get this diffraction pattern.
Right.
So light does the same thing. So you have to shape these little structures very specifically to direct that diffraction away from the optics of the telescope, or else you'll just get a bunch of diffracted light.
Okay.
And the coronagraph has a dark central region to block the light of the star, and then it passes through a washer-like ring that blocks most of the rest of the starlight. Okay. But there can be imperfections in the telescope's optics. So even when you turn up the brightness, even when you're detecting light, this very low level of light, you're still going to get this really mucky view that's caused by just imperfections in the telescope's mirrors.
Aww.
Even if we try and make it the most perfect we can, it's still going to have imperfections.
Even if we use robots to make it?
Even if we use robots. So there's another piece of a coronagraph it's a deformable mirror.
But wait, isn't that the problem with the mirror? It's deformed?
Yes. So we get another deformable mirror. This one, we control the deformations. So this one we place before the other components of the coronagraph, and it raises and lowers sections of the mirror to counteract or compensate for the telescope's optics. And it's controlled by a computer that's reading from the light sensing portion of the telescope.
Okay.
And it can compensate for most of those imperfections of the telescope's optics. And you can clear away most of that star muck. And that lets you see planets.
Wow.
And
like
I don't mean see planets like, oh, we can see the star wobbling around. No, you see the planet.
Wow.
You see the actual planet.
That's pretty cool.
That's so cool. And coronagraphs are based on this original invention that was used to look at the corona of our sun.
Is that why it's called coronagraph?
It is. So they way back before this thing was invented, when you wanted to look at the corona of the sun,
you just burned your eyes.
Hopefully you didn't do that.
Oh,
you would wait for an eclipse.
Right.
Which an eclipse is just one body blocking another, right?
Right.
So
for the eclipse method, you're waiting for the moon to go between the Earth and the sun.
Yes.
So then you can then see the corona.
Yeah, because the sun's light, the majority of the sun's light is blocked, and you're getting light that's from the corona of the sun.
Right.
So this guy, Bernard Lyot, I think, he was a French astronomer. It's Lyot. I'm not sure how to pronounce that.
Okay. It's probably Leo for
Leo,
if it's French. Right?
Maybe. However it's pronounced.
You wouldn't have a T and
Bernie.
Usually. Okay.
This guy Bernie.
Okay.
In 1931, he says, "Why don't I just make an artificial eclipse? Why don't I just put a little
dot
thing over the sun in my telescope, and then I can look at the corona?" And it totally worked, like perfectly.
Okay.
Well, not perfectly, because his was a circle, and
it can't
circles
be a circle?
you get that light diffraction, so it's a little mucky. It's better than looking directly at the sun.
So what do you have to do instead of a circle? It's not an oval.
Instead of
or
a circle,
just
you use these special shapes. I'm not sure what the shapes look like of a coronagraph, but you use these special shapes to direct the diffraction away. Because you can't eliminate diffraction. Light will always diffract.
Right.
But you can direct it away from your optics or from your instrumentation.
Okay.
So yeah, the deformable mirror we use to compensate for our crappy mirrors, and voila, we can see planets.
Wow. So
but
do we have like telescopes? Is it like ground-based telescope? Is it a space telescope? Like what?
Space telescopes.
So we actually have some out there that are like that?
Not yet.
Okay.
We're working on one.
Okay.
I think it's set for 2023.
Oh, wow.
I'm not sure.
It's a little ways off.
Yeah. That could be early. I can't remember.
Okay. So we're going into stuff that we actually haven't used yet.
Well, no, we've used coronagraphs. But the one that I'm describing, we haven't used yet.
Okay.
The one with these three parts that all work together.
Right.
JPL currently is working on it.
Okay.
But a coronagraph could just be a little disc.
Yeah.
Yeah. And we have
obviously
used those.
Just for looking at the sun. We've used a lot of. Yeah.
Yeah, but we've also used them to find planets.
Okay.
And then another way to do it, besides putting something inside your telescope, is to put something in front of your telescope called a star shade.
Okay. So this is just like shades you from stars.
It's basically a giant space umbrella that we use to see planets. Now, I do know...
How would a space umbrella work? Well, it's basically like the coronagraph, but outside the telescope.
It's just this big structure that you put outside of the telescope, very far away from the telescope. And it's about the size of like a baseball diamond, so it's big. It is very big.
Wow.
And it blocks the star's light just like the coronagraph does, except from much further away. So it needs to be much bigger. And I do know what the shape of a starshade is.
Yeah.
It kind of looks like a flower.
Ooh.
It's got these wavy petals.
It's a space flower?
Pretty much. It's a giant space flower.
Wow.
It's got these wavy petals, and those will redirect the diffracted light, and it creates this conical area behind the starshade where the diffraction is limited, and the telescope can see planets with minimal interference.
That's pretty cool.
So you don't need so much of the fancy machinery, but you do have to take this giant structure and put it way further away from your space telescope. So they're both pretty hard.
Yeah.
We got to be careful with that. If the solar wind is strong enough, it might flip your umbrella.
It's always a problem.
Might just carry you away.
Mary Poppins style.
So a starshade has the unfortunate side effect of when you want to look at a different star,
you have to move
you
that
need to
whole
move.
thing.
Yeah.
Wow.
You need to move your starshade over to that star.
Wow.
Yeah. So it's much more difficult to set up than a coronagraph, but it's a simpler concept.
Yeah.
So yeah, this method, the direct imaging, works a lot better than most of the other methods for finding planets that we're looking at their orbit face on. So like the top of the pancake.
Right.
And we can also detect rogue planets with direct imaging.
Ooh.
It's the only method that we can use to detect rogue planets is just looking at them.
Do we need any special... I mean, they're not near a star, right? So we don't need... Do we need?
They
any
have to be
special
really
stuff?
hot.
Okay.
We can't detect them if they're
They
cold.
have to be really sexy planets. Then we can detect them.
A planet
Maybe.
in some nice lingerie.
That's right.
So that is the end of our methods of planet detection. Our current methods that have actually detected planets.
Right, except the starshade, because I don't think we've done that yet, right? Have we?
Not yet.
No.
Working on it.
But methods that
we're working on them. Yeah,
we have determined will work.
Yes. Yeah.
Right.
We have done direct imaging, and this is just an extension of direct imaging.
Oh, that's true.
Yeah.
Yeah.
So are there any questions from our audience?
Okay, so if tomorrow I wanted to just, go out and try to discover a planet, what do you say is, like, the best method if I wanted to do that?
If you wanted to do it tomorrow, or you wanted to start tomorrow and you got a few years to kill?
Yeah, if I wanted to start tomorrow.
Right now, the best method is the transit method. It
method.
has found the most planets.
I see.
But that's limited to edge-on systems.
Yeah, you can only see
Because it has
planets
to
that are
transit.
edge-on.
That's fine. Just
Exactly edge-on.
If I just wanted to, like, had the best shot at just discovering a planet, I found that planet.
Well, unless you can build a giant space telescope, you're probably not going to find one with the transit method. I would say your best shot is direct imaging then, because you can find really hot, far planets with relatively inexpensive equipment.
I see.
Like millions of dollars? Thousands of dollars?
Millions.
Millions of dollars.
Millions of dollars.
So if you're a millionaire and want to find some planets, but then you can name the planets after whatever you want.
It's not a multi-billion-dollar space telescope.
Well, that's true.
Yeah.
It's a bargain. And if you do find it, name it something better than 786B712.
Name it Planet McPlanetface.
I'm surprised there isn't a planet named that yet.
That's what
And
I would name my planet.
It should be orbiting Starry McStarface.
I think NASA's smart enough not to open that up to the internet.
Any more questions?
I think you've covered all there is to know about planets.
Planet hunting.
Planet hunting.
There is so much more to know about planets, and it is fascinating.
Yeah.
Oh, we should do an episode on tectonic plates.
Yeah,
They're fascinating. They're super fascinating.
People didn't believe that for years. They knew it was a thing, and because
They were like, that's not true.
That's not true.
Entire continents can't move. And then we were like, but look at all the new crust material in the ocean. And they're like,
that's the ocean. That doesn't count.
But
ocean can't be in a continent.
A bunch of crusty people were not a
fan. Yeah.
But all those mantly people were.
They were all for it.
Yep.
I was just waiting. We need a badunch.
We can add that in post, right?
Yeah. Because we need about 30 of those.
Well, if there are no more questions, then that will wrap up our episode on planet hunting.
All right.
Thank you, Matt.
Thank you, Hunter.
And we want to thank Cyber SDF for letting us use their songs Welcome and Mellow Acid as the intro and outro of our podcast. And we especially want to thank our studio audience.
Woo!
And I hope you were paying attention to each one of those planet names, because they will all be on the test.
No!
Including the number ones?
Yep.
Yes.
Especially the number ones.
Especially the number ones.
Encyclopedia Podcastica is a production of the Silicon Valley Skeptics, an organization dedicated to promoting science and critical thinking. You can find us on Twitter at SVSkeptics or Facebook at facebook.com/SVSkeptics. You can contact us at svskeptics@gmail.com. If you like the show, please rate us on iTunes.